Good evening, dear students. So far we are discussing in a kinetic theory. We are going to see today now what is the rate, then rate law, order, then molecularity, finally factors affecting the rate of the reaction. Factors affecting the rate of the reaction. So these are the points which we are going to see now. There is a rate law, order, molecularity, and the factors affecting the rate of the reaction. One by one we can see. First of all, rate. Rate is nothing but a speed of the reaction. How the speed of the reaction is proceed. How the speed when a reactant become a product. That can be given as a formula. Unit of concentration by unit of time. That is a rate. Simply we can say that is a change in concentration per unit time. That is called rate. Change in concentration per unit time. For example, we can have an equation x times of A plus y times of B is the product. Okay. Now let me write the rate equation. That is rate law. Rate equal to rate that is equal to K into concentration of A power m and the concentration of B power n. This is called the rate law. This is called the rate law equation or rate law. What do you mean by rate law, sir? The rate law, the law which relates rate and the rate constant and the concentration of the reactant. That is called a rate law. The law which relates rate constant and the concentration of the reactant. Okay, that is called a rate law. From this we can calculate the rate constant. From the rate law, rate by concentration of A and B, it will give a rate constant. Okay, rate constant. Okay. So here concentration A, concentration B, m is the order. Then m is the order with respect to A. N is the order with respect to B. So in the reaction, what is the order of the A they asked, that is M. What is the order of B they asked, N. What is the overall order? The overall order is nothing but a M is N. From this now I am going to define what is the order. Okay, what is the order mean? It is nothing but the exponential power of the concentration term in a rate law, the experimented rate law. Okay, order is nothing but a sum of the exponential power of the concentration of the reactant in rate law. Rate law means that is experimental data. From this we can understand that order cannot be stoichiometrically, we can say it is only experimented data. Order is nothing but that is a experimented data. That's why we can define the order. It is the sum of the power that raised in the concentration in a rate law equation. Okay, that is the order. Now, for example, yesterday also you have seen that cyclopropane, we can write the rate relation for cyclopropane. While heating, it gives a propane. Okay. So how we can write the rate expression for this? Rate equal to rate that is equal to K, the rate constant, and the concentration of cyclopropane. Concentration of cyclopropane. It is experimental value. I cannot write simply 1 or 2. That is the experimental data that I already mentioned. There is known data, that is 1. It means the order of the reaction when a cyclopropane is converted to propene, the order of the reaction is 1. Okay. At that instant means at a time. For 1 minute what happened, 2 minutes what happened, or 3 minutes what happened. So different time interval you will have a different concentration. That is you have to write here. Okay. Then how the problems may be asked in a NEET or in a state board question related with the rate expression. Simply they will give a rate. Before that you should know what are the factors. Rate is one factor, rate constant is another factor, then concentration of the reactant is another factor, and the order. There are 4 factors are there. Among the 4, they will be giving 3 of them. They will ask 1. For example, if you want the rate, they are giving a rate constant value and the concentration of the reactant, and the order will be given. From this data, from all those 3 data, you can calculate the rate. If they want the rate constant K, you need K value, then they will give a rate value. From this, how we can get a K value, rate constant K, you want that rate divided by the concentration of cyclopropane. Okay. The triangle in chemistry, it shows that a cyclopropane. In each corner, there will be CH2, 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 CH2. This is called cyclopropane. For simplifying that, they will give a triangle shape. Okay, from this also we can get a rate constant. From this we can get the order also. For at an instant, different instant they give, you can get a order also from this relation. So the rate law expression is very, very important. Once again I am getting this from what is the rate, speed of the reaction. What do you mean by speed of the reaction? How the reactant become a product at a time. If our reaction carried out for simply we can say cooking process. Okay, we are taking a rice and water, we are getting into the boil. At 5 minutes, what will happen? The small amount of the rice will become getting to the food like after 10 minutes, after 15 minutes. So that is called instant, at an instant. At 5 minutes, if you check over, if you put a time there is in the formula, there is a concentration of food, then at a time, 5 minutes, you will get that. For example, if I am taking that, what happened to the reactant? Reactant is decreases. So, if you get a 1 kg of rice, that is becoming food. The reaction only depend upon the reactant pieces. What happened after 5 minutes? The 1 kg of rice will maybe become a 750 grams. 250 grams is converted to food. That is a product. After, there is 5 minutes. After 10 minutes, if you see, 50 gram of the rice will be available. 500 gram of rice will be available, or 500 gram become a food. After 20 minutes, there is no rice at all. Everything become a food material. That is will become a 100 gram, 1000 gram. So what happened here? Decreases the concentration of reactant, at the same time increases the concentration of the product. That way we can calculate this. After that, rate expression, the rate law. Rate law is nothing but the relation which the law which gives the relation between the rate constant and the concentration of reactant. Okay. From this we can calculate the rate constant. Rate constant is nothing but a K. K can be getting from that rate by concentration. Okay. Then order. Order is nothing but it is sum of the powers of the concentration in a rate law. That is not a theoretical data, that is experimental data. Now let us see the comparison between the rate and rate constant. rate and the rate constant. It is a speed of the reaction, how the reactant becomes product. R means reactant, P means product. It is speed of the reaction, how the reaction becoming a product. It is simply constant, that is a proportionality constant. Second point, it is measured as decreases in the concentration of reactant. The concentration we can say that within the bracket. If anything within the bracket is given, that is considered as a concentration. Concentration R means reactant. That is measured as decreases in the concentration of reactant or otherwise increases in the concentration of P. What do you mean by P here? Product. It is measured as decreases in the concentration of reactant, or it is measured as the increases in the concentration of product. Whereas it is equal to rate of the reaction, or it is equal to rate when each reactant concentration or unity. So for example, let me explain this. What is the rate expression? Rate equal to rate constant in the concentration of A and B. What it mean? Each reactant concentration or unity. Unity means 1. Then K 1 into 1. So now rate equal to K. That means when the reaction concentrations are unity, rate equal to rate constant. K is a rate constant. When a rate equal to rate constant, when not all time, when the reactant pieces concentrations are unity. Then point number 3, we can say it depends on initial concentration. Rate depends upon the initial concentration, whereas a rate constant does not depend on the initial concentration. So this way we can compare. It is the speed of the reaction, how reactant becomes product, whereas it is simply proportionality constant. Then it is measured as the decreases in the concentration of reactant or increases in the concentration of product. Whereas rate constant is equal to when each reactant concentrations are unity. For example, we can relate this. Then the rate always depends on the initial concentration of reactant, which is taken in a reaction. It does not depend on the initial concentration. This is comparison between the rate and rate constant. Then let us see the molecularity. Molecularity is nothing but a total number of species involved in elementary step. Elementary steps of the reaction. Total number of pieces means the total number of reactant pieces involved in the elementary step. That is called molecularity. Then your question may ask, what is the elementary step? Let me explain. Elementary reaction or elementary step. This is each and every single step in a reaction mechanism. Each and every single step in a reaction mechanism is called a elementary step. Each and every single step in a reaction mechanism is called a elementary step. What is the molecularity? Molecularity is nothing but a total number of pieces, that is reactant pieces, involved in the elementary step, that is called molecularity. Then what is the elementary step? Each and every single step in a reaction mechanism. Let me have a example for this. We can take a decomposition of peroxide in the presence of iodine. Decomposition of peroxide in the presence of iodine. This iodine we can take 2H2O plus O. This is a balanced reaction. Okay. Now, what the first step one? What happened? In step one, what is happening? One peroxide molecule. Iodine is a catalyst. Treated with the iodine, that's I minus iodide, you have to say. Generally they will say iodine. The catalyst, you are getting that H2O plus OI minus. This is the first step. In step 2, in the step 2, you are having that one more peroxide is treated with the OI minus. OI minus is giving H2O and O2. Okay. Then overall reaction. You want to have overall reaction. See, O minus cancel, OI minus cancel. You are getting that plus I minus will be here. I minus will be cancelled. Then 2 times of H2O2 gives 2H2O plus O2. So this is the equation I have written in the first. This is overall reaction. This is how the reaction is favored. This is called reaction mechanism. Step by step process. Suddenly it will not happen. This is a way how the reactant becomes product. This is called reaction mechanism. Okay. In this mechanism, each and every single step is called a elementary step. This is a separate elementary step. This is a separate elementary step. So each and every single step is called a elementary step. For this example, peroxide decomposed by the iodide catalyst, you are getting that water and oxygen. This is a reaction. Simply it will not happen. Suddenly the peroxide will not become a water and oxygen. First peroxide is treated with catalyst iodine, that is I minus, you are getting that water and OI minus. Then again we are taking 2 moles, no, the second mole of peroxide is treated with OI minus to give a water and oxygen and I minus. So net overall reaction, this is called overall reaction. Here 2 times of peroxide is there, remaining things are cancelled both sides. So water and oxygen, this is a step overall reaction. Here, which is a rate determining step. So there may be this is 2-step reaction. In some complex reaction, you have 3, 4, 5 steps also will be there to get a final reaction. On those cases, all reaction will not determine the rate of the reaction. Okay. There will be a particular reaction will determine the rate of the reaction. This is called, in this 2-step, the first step will be the rate determining step. About this, the activation energy and all those things, in next topic you will see detailing. Just I am mentioning that what is called rate determining step. The overall reaction may have several steps of the reactions. Among them, any one of will be the rate determining step. Okay, that step is mostly that step will happen very slowly. So we can logically we can say the slow step will be the rate determining step. In this 2-step, this is a rate determining step. So in that rate determining step, what is happened? What is the molecularity? Total number of pieces, reactant pieces involved in the elementary step. So considering this is the overall reaction, this is the rate determining step. Here what are the particles involved? Peroxide 1, I minus 1, so totally 2. That's why this reaction is bimolecular reaction or molecularity 2. Bimolecular reaction or molecularity 2. Why I am saying this molecularity 2? Or I am not simply seeing the 2 times of peroxide, I am saying This is after writing the mechanism of the reaction. In that mechanism of the reaction, which is a rate determining step, we need to find. In the rate determining step, total number of pieces, that is reactant pieces involved in the elementary step, that is called molecularity. So this is bimolecular reaction. Decomposition of peroxide in the presence of iodine is called a bimolecular reaction, because this molecularity 2, in those reactions, the peroxide and iodine both are involved. So this is molecularity 2. Now I hope that you are understanding what is called molecularity. Okay. Then let us see about the comparison between the molecularity and the order. Order and the molecularity. Order and the molecularity. This is a comparison which we are going to see now. What is the order? Already I explained that it is sum of the power of the reactant concentration of reactant in a rate law. Sum of the concentration, it is sum of the powers of the concentration of reactant in a rate law. Okay. Rate law, if you see the how the reactant, you can see in the product side. For example, if you see X times of A plus Y times of B, it gives a product, the rate expression. If you write the product rate expression may be K rate equal to, this is rate law for this reaction, K concentration of A power X, concentration of B power, that is maybe M or M. This is called the order of the reaction. And the experimental rate law, determined rate law. Why I am mentioning the experimental data? It cannot be given as stoichiometric. If I say, for example, 2A plus 3B gives 5C. If I say writing like this, then rate expression you are going to write rate, that is equal to K concentration of A. You can simply write power 2. You cannot easily simply write. That is the 2. That is not stoichiometric. It should be determined experimented. Simply you cannot 2 is there. I cannot put 2. Then B power 3 you cannot put. That is experimental data. You need to find by the experiment only. That's why experimental data. Molecularity. Already molecularity is there. It is a total number of pieces involved. The same I cannot repeatedly. It is no necessary to write. Total number of pieces that is involved in an elementary step. If the question has to define molecularity and define order, that is the first point. That may be comparison between these two. Then second point, if you go, it is it may be, it can be or may be 0 or fractional or integer. The order may be 0 order reaction available, fractional order also available, integer also available here. But whereas it cannot be 0 or a fraction. Molecularity never be a 0 and a fractional. That is the meaning here. Molecularity cannot be a 0 or a fractional. But order of the reaction may be 0 or fractional or maybe integer. It is assigned for overall reaction. It is assigned for an overall reaction. Complete. See here, the order can be complete for the overall reaction. For this overall order, it is assigned for the overall reaction. That is order. Whereas molecularity assigned for a elementary step, each elementary step. It is assigned for each elementary step. Individually. See, this is here 2, here different. So that is individually, each and every elementary step having the different molecularity. Okay. But order, that is overall order, you can say. For the reaction, you cannot say what is the molecularity. No particular step you have to say the molecularity. For step 1 molecularity this, for step 2 molecularity this. But whereas the order of the reaction, if they asked, overall order will be assigned. Order will be overall order can be given. But this is elementary step only. The molecularity only for a elementary step. Okay. Now it's clear. Let us move on to the factors affecting. Now let us see the factors affecting rate of the reaction. What are the factors can be affecting the rate of the reaction? First one, nature and the state of the reactant. Then concentration of reactant. Then surface area of the reactant. Then temperature. Finally, catalyst. These are the 5 factors which affect the rate of the reaction. Now let me explain one by one. Let us go with the nature and state of the reactant. See, we cannot see all the reaction with the same speed. We cannot expect all the reaction can happen in the same speed. Or otherwise, as you said, if I am teaching, all the here 50 students are there, all can understand at each time. No, but once there are few can understand. By repeatedly I am teaching, then you can get it. Likewise, you cannot expect all the, even though same teachers, same students, it cannot reach at a even. So, the different reaction, they will have a different rate, first of all. The rate, because of the nature of the reactant, there will be one brilliant will be there will be some slow learner will be there, all are okay. But for them, that is way of teaching will be something different. So, the time taken, at a second, they can catch up someone will catch too many repeatedly teaching, then only they can get it. Likewise, in a chemical reaction, there is a sudden reaction that's all possible. It will take slowly, too long it will take, even year by year there is a reaction is going on. At a fraction of second also there is a reaction. So, it is depend upon the nature and state of the reactant. For example, the redox reaction FAS versus KMNO4. This is a redox reaction. It is happening and very fast it can happen. Same KMNO4 when it is treated with the oxalic acid. Oxalic acid versus this also redox reaction, the same oxidizing process, but it will take it cannot take simply. The heating is required. Simply you can add these two, they will combine together, the reaction is formed. Whereas oxalic acid, the nature of the oxalic acid and the KMNO4, this is also redox, but it can take more time. Even it should be heated. After heating only we can have to mix, then only the reaction will be proceed. Okay, likewise. Then let me give another example for the state of the reactant. For same purpose, formation of potassium iodide plus lead nitrate. Lead nitrate, when it is combined together to give a lead iodide plus potassium nitrate. So here, see, this is the example for a state of the reaction. If both are in a solid form, the lead iodide, yellow color precipitate, lead iodide will form very slowly, or less amount of lead iodide will be formed. Okay. For example, if you take the test tube, you put a Ka plus lead nitrate there. When both are in a solid nature, it will consume time. The same case, the same Ka plus lead nitrate in the liquid form, the aqueous form, if you take the yellow color precipitate form very instant, at a sudden, when it pour itself, you may find the yellow color precipitate. So here, same reactant, but the reaction is very slow. but the same reaction, but the reaction is very fast. What is the difference between these two? If you say all are solid, or the reactant pieces are solid in nature, it consumes lot time. They do not react. Whereas they are in the liquid form, they are very fast at reaction. Same reactant, same product, you are getting a time. Okay. So the state of the reactant also causes. So the scientists experiment that they are giving, if a reactant is a gaseous form, it is too fast to react. Whereas liquid less than that gaseous, or solid is be very less than that. For simple, I can give an example for a cold or a sneezing problem. If you take a tablet, it may take 2 or 3 hours to cure. If you take syrup, 10 to 15 minutes you can have a relief. But you have vapor, inhaler, at a sudden relief you may causes. Okay? Sudden relief you can feel it. So this is the difference. The state, how different, same chemical, there is no different chemicals is there. The same chemical, same the expended in the body, you can have a tablet form, you will have time, maybe 1 hour, 2 hours. But liquid half an hour, the syrup sometimes, if you take a vapor form, it will very, at a sudden relief you can feel it. That's why the rate of the reaction is depend upon the nature and the state of the reactant. And then concentration. The higher concentration, the same example let me give. If the concentration is more, 250, 500, if you more concentration, more reaction. Why sir? If concentration increases, rate also increases. Okay, this is concentration, rate also increases. That is the relation. Whenever concentration of reactant increases, the rate is increases. Why? Because when a concentration increases, the colliding particle will be more. Number of colliding particle will be more. Then more colliding particle, more collision is possible. More collision, the reaction will be faster. Whenever the collision is more, the reaction will be faster. That's why when the concentration increases, then you can have a reaction is faster. Okay. Then let us move on to surface area. Surface area increases. Surface area increases, rate also increases. Surface area increases. Whenever surface area increases, rate also increases. For a simple example, I can give you are preparing dosa, no? The uttapam they call it. With a cup of flour, the same time it consumes lot of time. The same cup of flour, when it becomes a dosa or uttapam, it takes 5 minutes, 3 minutes. But the same cup of flour, when you would spread over in the plate, it take at the second after putting that the master will take the roast it. Okay. See, the same amount of heat is supplied, but the same amount of reactant is supplied. But what is the change in between these two? This is the area, surface area of the reactant is less here. But whereas the surface area of the roasted it is more. That's why surface area increases, rate also increases. Till more I can give an explanation. If you drink a tablet, for children and all, if you cannot give a tablet like this, they will crush it. They will make into the powder. The same amount of tablet, if half tablet is broken, they will not give simply. They crush into the powder, they will give to them. When it is crushed into the powder, the solid form, when it is crushed, the more number of surface area it will occupy. See, for example, if you take a tablet there, if you keep it here, the tablet may be size occupying the place here. The same tablet, this piece of tablet is crushed into, if you keep in the paper or plate, it will consume this much space. The space is enlarged, the same amount. The quantity is not changed, but the area covered. So here, each and every particle will undergoing the reaction. Each and every particle undergoing the reaction at the same time. So more number of particles may involve when the surface area increases. Okay. When I slap with one finger, you will have a pain very less. The same time, the 4 fingers is used to slap. Now surface area is increased. You may feel a more pain. That is surface area increases, rate of the reaction increases. Then temperature. Whenever temperature increases, the rate of the reaction also increases. All these 3 cases, both of them increases. Temperature increases and the rate of the reaction increases. For example, if a tumbler of water you have 100 ml tumbler, you will water, ordinary water, I ask to put your finger into that, you will put slowly and take away. Okay, the same 100 ml water, it is boiled water mean, same 100 ml, I ask to put your finger and take out. No. At a sudden, when you keep it, you will get out. That is first of the reaction here. See, here what is changed? Same 100 ml water. What is there? I am asking you to put your finger there. You are putting, even I asked to take also, you will slowly you take. There is no changes. Very slow process you will take. If I asked or I am not asking you, you will take slowly. There is no carrying it. Whereas the same hot water, the temperature is rises. When you pour, at a sudden you are keeping out. There is a physical example I am saying. When a heat is increases, what happens? The process is very speed. Occurring speed is more. Likewise in chemistry, in chemicals, wherever temperature increases, the reaction also increases. The rate of the reaction increases. For example, the same tablet example we can take. Always you take the medicine in a hot water, they say, or simply warm water. Don't take any medicines in a cold water. Why? Because the reactant pieces, the chemical pieces inside the tablet or any medicine you are taking, it do not react. If you take cold water, when the temperature is very low, the reaction time may be taking 2 more. It will dissolve in water, no worry. But it will take more time. If it is in a hot water, it can easily pick up, straightly concentrate on the reaction. Then it will be faster. For a simple example, likewise, these are physical oral example for your understanding purpose I am saying, but in depth you are involved into the chemistry. In a chemical reaction, see for many reactions I can give examples like when simply you put many compound will not treated with water, they will dissolve slowly. If it is added in hot water, it will go, or when you heat it up, the reaction is easily or too much faster. That's why temperature increases, rate of the reaction increases. And finally, we are going to the catalyst. What is called catalyst, sir? Catalyst nothing but a substance which enhances the rate of the reaction or which alter the rate of the reaction. On those days, the mere definition, it enhances the rate of the reaction. Nowadays, we have negative catalyst also. So, you cannot say that is enhance the rate of the, it alters the substance, the pinch of a small amount of substance which alter the rate of the reaction is called a catalyst. The small amount or pinch of the substance which alter the rate of the reaction without disturbing the reaction. That is very, very important. The catalyst should enhance or speed up, or that after the reaction is over, it should come out without disturbing the reaction. For example, what is happening, sir, there when a catalyst is added? See here, the peroxide example also we can have. Peroxide dissociated to water and oxygen. This is the example we have already seen. The same example I am taking. Where why I need to I minus is catalyst. After last of the reaction, overall reaction, you cannot find the I. You know, what is the overall reaction? 2-step or final step, the I is going out. That is must. That is, catalyst should not involve into the reaction, but it should alter or enhance the reaction. What happening, sir, while you add the catalyst? It's a chemical term. The activation energy decreases. That is the reaction coordinate or reaction proceed like that. There is potential energy. If you say these are Arrhenius theory, you will study in coming classes. For this explaining catalyst, I am just what is the how the catalyst enhances the reaction. For example, this is reaction coordinate. They are likewise concentration of reactant. This is concentration of product. This is the energy barrier. This is called EA, energy barrier or activation energy. EA is nothing but a energy barrier or activation energy. See, what is that? Simply you are writing a graph like curve. You are simply saying EA. So I am explaining you that is a reactant. When a reactant, potential energy, you have to apply the energy in the form of heat or light, anything you are applying the energy. After consuming the energy, this is called a energy of colliding particle. This graph in the area, this energy of colliding particle, that is reactant. When it absorbs some energy, it should need to become reach a threshold energy. This is called threshold energy. While it reaches threshold energy, after reaching on the threshold energy, this is a equilibrium point. It may go down or again it can reverse to the reactant. Which substance reaches the threshold energy, after it will become a product. Okay. For that, each and every pieces should reach the threshold energy. Threshold energy is now already energy possessed by the reactant, that is the energy of colliding particle. Already some energy is possessed by the reactant. That is not sufficient to become a product. So they need some additional energy to reach threshold energy to become a product. Each and every reactant, they need some additional energy, that is called activation energy. Energy which is activating, that is called additional energy. The additional energy required by the reactant, that is called activation energy. If activation energy is more, for example, I am drawing this graph, the activation energy is more, so the reaction will be very slow. The activation energy is greater, reaction will be slow reaction. So the activation energy is reduced or very less, EA is very less, then the reaction will be very fast. This is the logic. Let me give some common colloquial example. Both of you have 100 rupees. You are going for theatre. Okay, that is the 100 rupees is our consideration. That is your colliding energy of colliding particle. That is the money possessed by you. That is energy possessed by the reactant. That is 100 rupees each of you. Okay. Let me change this. 1 and 2. Your friend having 110. You are having 100 rupees. That will be nice. I can relate easily. But the theatre price is the ticket rate is 120. You are having 100. Your friend having 110. But the ticket rate is 120. So you need the 120 is threshold energy when you enter into theatre. That is 120 is a threshold energy. But you are possessing a 100. Your friend is possessing a 110. Who can easily, both of you cannot get into without 120. But there is a possibility, probability, if you can get 10 rupees, you can go easily. But for you, you need a 20 rupees. So this is the activation energy. You need a 20 rupees, you have your activation energy is more. But you have less probability getting into the theatre. But your friend only he need a 10 rupees. Or otherwise if he possesses 120, he can easily enter. This way, each and every reactant will have some particular energy, that is called the energy of the colliding particle. But it needs some threshold energy that you need to gain from other sources. What are the sources? Heat, light, electrical, these sources you should possess. And that the energy difference between the threshold and energy of colliding particle, that is called activation energy, or additional energy required. The additional amount required to you, that is need to get into theatre is 20 mean your activation energy is 20. Likewise, each reactant will have some activation energy. When we are comparing 1 2, no? For your friend 10 rupees needed, for you 20 rupees needed. Who can easily enter? Your friend, okay? Because he need only 10 rupees. Likewise, when EA activation energy increases, reaction will be very slow. When activation energy decreases, reaction is very fast. Sir, that is something different. What happened to the catalyst, sir? You are saying story and all. Come to the catalyst, sir. What is doing the catalyst? What is the role of the catalyst there? This is altering. That is a general definition. Is we are saying that alter the rate of the reaction. For example, when you add a catalyst to that reactant, normally this is EA. After adding the catalyst, this will be EA. For example, you need that much amount of EA without catalyst. The reaction may carried out, but you need this much amount. The second curve is there. No, this curve shows that presence of catalyst. After adding catalyst, this curve become very small. That means the activation energy is reduced. What is the role of activation? Simply, it alter the activation energy. it reduces the activation energy. When activation energy is less, what will happen? Reaction will be fast. That's the way how the rate of the reaction is affected by catalyst. The catalyst are also very, very important to alter the rate of the reaction. Once again, I am repeating, what are the factors which are affecting the rate of the reactions? Nature and state of the reactant. Another one, concentration of the reactant, surface area, temperature, catalyst. These are the 5 factors which are affecting the rate of the reaction. Okay.